All right, so this is our weekly seminar, and today we're covering quite a bunch of ground to get to the thing, where this thing is actually where's the thing, where this thing is the latest result by Anthropic, and like I'd like to um, I just like to go through why we care, and then like try to pinpoint where exactly their work is in the space of like all possible works, and then like get to the meat of it. So why we care is that an interpretability approach which looked cool, but previously only worked on very much toy models, scaled to a GPT-3 class model, which is a large model. And like this was quite non-obvious because the way this work started is from people considering that each individual neuron might be semantically meaningful. And like a toy model might have 100 neurons, but production models have billions. So that was why it was unclear it would scale. And like the people have a website where they document this kind of expedition, in this particular research agenda. And what I'd like to do now is to look at this model of a transformer and kind of try to say what kind of interpretability works applies to what part of the transformer. So let's go through the scheme. Like we have an input, we get an embedding from the input. For practical purposes, we can treat these first two embeddings as the same. Then we do attention, which in practical terms means we have three learned matrices, and we multiply the inputs by them to get the attention output. And then we have a linear layer after the attention layer. And these dashed blocks, we have a bunch. These are called attention heads. Yeah, and there are details in the implementation, but they're not important to us right now because what we only care about here is like which matrices are there and how the data flows between them. And the very earliest works in interpreting language models, I think, go by the name of bitology, by Bird, the model. And let me just show you some pretty pictures. So, like, here is one early result in Bertology. This is a visualization of attention weights. So this is attention output here. And what we're saying, like the vertical axis is a French sentence, the horizontal axis is an English sentence, I mean words in a sentence. And what we're seeing is that this is a machine translation task. Like some words are easy to translate, like to translate the into le, you only need this one word. And some words need context because like area might translate to different words, like it's apparently zone economic or something. I don't know how you like where you put the stress actually, but anyhow, so like area might translate differently, so you look at other words in the sentence to know how to translate correctly. And like this is kind of like this picture is often shown as a pro of attention, like that it allows us to learn this kind of like mapping, which is important for which. But what I'd like to point to is that this result in visualizing attention came after we successfully used attention. So like post hoc, we figured out post hoc we figured out that actually attention seems to encode something like semantically meaningful. And like to really ground this semantic meaningfulness down, here is another like very classic result. So this is an attention head which we empirically confirmed. Like this was not like pre-trained, like no particular bias towards that, like just an empirical fact that when we learned a normal language model on a normal language data set, an attention head learned this kind of correspondence. So like on the left-hand side, we have subjects, on the downside, we have verbs. So like that makes like this is, I guess, inverted, like you heard. So like this is like what we get empirically is a head that is like this kind of block specialized in this kind of correspondence. And the hand wavy explanation is that apparently this is useful for downstream tasks, right? So like this kind of and like you might even think that maybe this is some sort of like universal truth about the language, that this is useful to know, to reason about language, like for downstream tasks like extract entities or translate or like stuff and things. So are we clear so far? I'm saying something skeptical. All right. Okay, so and there is another result. I'm not going to cover it today, but the result is that I think I have another person who would join us. Yeah. So another result is that so like what we just looked like are like simple heads, which like do something which is like straightforward syntax parsing. Like okay. There is also a result that heads can be very complicated, and like for instance, you can have heads which form an automata which can output a structured language, for instance. So like like to write HTML, you need to understand like its rules, and this can also be implemented as heads or like a number of heads. So like this is looking at this part of the picture, at attention output. You can do something else. You can look at output of the linear layer, and this is the probes literature. The way this normally works is you just fit another layer here, which is a classifier. Oh, I mean, not here, as in it doesn't go through like here, as in you fit a classifier based on the linear output, and you might ask like, what if we train the classifier on? And I say we make like a special purpose data set which is supposed to elicit whatever we're looking for. For example, we might have like 100 positive sentences or 100 negative sentences, and we are like, can a classifier which we fit at this particular like layer in this particular like head distinguish between the two? And if it can, then we are like, okay, this is represented here.
or before.
And we can ablate to find out where. Yeah, so that's a probe. These two things I'll go over later with more detail. I think let me do circuits first because I have pictures. Pictures, and I have them here. Yeah, so this work is on CNNs, so not transformers, another architecture. And yeah, let me kind of hand wave for a minute before I go to the pictures. So the idea of circuits is that you're like, okay, like maybe one neuron is semantically meaningful, and maybe like a network of neurons are semantically meaningful. And like at least in animals, we have results about networks of neurons being semantically meaningful, and so we're like, okay. And this kind of this goes in this good tradition of trying to reverse engineer convolutional networks, where we can so a convolutional network is engineered as a bunch of layers in which we have in this picture apparently smaller and smaller convolutions, which is weird. Yeah, in which you have larger and larger convolutions, and the early researchers found that if you just look at those maps, as in if you look at those weight matrices, they seem to do something. And if you train on a toy data set of cats versus dogs, you can kind of, if you squint, see that this kind of looks like a cat ear, and this kind of looks like a tail or something. And so what future work did is try to run the network in reverse. So we normally train weight to minimize loss. And what this work did, this was Google Deep Dream. They tried to freeze the weights and minimize loss and generate the input. Okay, that makes sense. Normally you change the weights and you have a fixed input, and now you freeze the weights and you generate the input, and you're still minimizing loss. And they came up with all kind of weird pictures. Yeah, so it's a genre by now. And if you try to apply a computer science mindset to whatever is going on here, then you kind of get this circuits paper. And so the authors say that if we try to figure out what's going on here, we see that we have curves, we have circle spirals, we have we have my Zoom misbehaving. Yeah, so and basically they say that that these things work as detectors. So if we have a curve like this, then it's activated for a curve in the same direction, and it is inhibited for a curve in a different direction, and that basically we have a complete set of curves, and from those curves we assemble something more semantically meaningful, like an oriented Docker detection. So with me so far, this Make sense? Like you can kind of you
can I try to explain it in my own words and see if like everybody are on the same page quickly?
Yeah, sure.
So do I get it right? The study about circuits is essentially that we like treat parts of big network as like, well, this is small subnetwork that does something. And the idea in CNNs here is that we have inside a big network that can distinguish like cats from dogs. We have small networks that can distinguish, that work like filters essentially. And you see for them the original emissions, like, does it fit? Does it no? And if the like initial image, input image is does fit like the filter that we have, we get like larger output. If it doesn't, then we only have like a small part of it colored.
Yeah, so
that's how it works.
So the idea is that if you just look at the network naively, then you see like a big neural soup, and this suggests that maybe you actually have like curve detector 1, curve detector 2, and like from this 2 you get like a dog head detector, and like from this you get a dog detector. So like as the semantically meaningful hierarchical something. I think this thread. Yeah. So the next work in the sequence introduced the induction heads actually. Okay, that was circuits. And circuits work on. Actually, circuits don't work on this picture exactly because they were they were originally envisioned for CNNs, and this is transform architecture. But if they did, they would work on linear output, like this is like direct translation, and circuits as introduced here were work on attention heads, and this is the induction head result. So this is kind of again about like seeing a part of the model as something semantically meaningful. Okay, so before we go to the main event of today, I'd like to start with another paper, which is also interesting and like just short to cover. And I think I have a blog post here somewhere. Steering. And I open the PDF file. Yep. So this is 2023 work. The essential premise of which is you have GPT-2 and you add a vector to the activations, and this changes the model's behavior in a useful way. So like you can have, like here they show a love vector, which gives a kind of a stupid answer in this case, but anyway. So the maybe another picture to start with here. So in preparation for this seminar, I prepared this, and like one of the questions which like are pertinent in the literature is we have all those boxes on the diagram, like have key query value, like output this, output that, embeddings. And the question is which to patch. And this paper patches activations. That is, it intervenes in it intervenes like in the arrows, I guess, in this diagram. Or like in the, this would be like f of wx and we patch we do G of f of wx. So we wrap the arrow in something. And like to talk about this, it's kind of useful to talk about what we expect to see in the activation space. And like, again, there is prior work suggesting that something is happening there. Like there is prior work which does this, right? So like the famous result, we teach, we learn word embeddings, as this is the word2vec paper, and the embeddings have this property that this is actually so I think the original word2vec paper only claims this property, but later researchers also showed that. So the original word2vec paper claims this property. Actually, it claims something else entirely. I'm sorry. So the original word2vec paper claimed that if you have king and we say king minus man plus woman is queen, or like we have Paris and we say minus France plus Russia, we get Moscow. And this is like interesting by itself because it says that in our like 300 dimensional embedding space, like distances are meaningful to humans. And further research showed that we have something even stronger. We have that you can go in a particular direction. Like we have points, these are our words, and you can go a constant direction from a word and get something. Like here, blue is a gender swap vector. So like if we go a constant direction from any word, we get its gender swapped version, or like in this case, like female version. Or what this picture shows is that the red vector is a plurality vector. Like if we go from any word in the direction of this vector, we get the plural version of the concept. And like this is extremely not obvious, I think, that this property holds. But it does in simple natural language embeddings, as used in like I think this work is like 2018 maybe. I think I should actually have it here. Yeah, this work. Oh, this work is 2013. All right. Yeah, word2vec is old. I think word2vec is 2012. Yeah, like this is old style embeddings. Very cool semantic properties. And here is something for CNNs, I think. Oh, well, for pictures anyhow. So like we have a model trained on pictures, and we found a vector which, depending on its magnitude, makes the person smile harder. And like, again, extremely not obvious this should happen. There's a similar result in reinforcement learning, which I can't explain, so I won't talk about it. And now, like, now that we have this kind of intuition why this might even work, let's see how this might work in GPT class things. And like, this is a little simplified because like we just like kind of folded the dimensions. Our embedding here is one dimensional, not like 1600 dimensional as it would be in GPT-2. But like, what's going on here? We take a sentence which goes like, I love dogs. This is padding, unimportant. So first we do the embedding. We get numbers for each of the tokens. and like then we do a forward pass, whatever, and we get an output which is like whatever. I'm not sure what the task here is. Yeah. Anyway, this is like technical something. Now, like the question is, how do we patch this thing? Like we want to find this like magic vector which will change the outputs. And the way we do that is we first do another forward pass for like our for the thing we want to steer towards the direction of, in this case wedding, and we arbitrarily pick that we are going to patch at layer 6. And then what we're gonna do is we like just add the things together, add the activations together at layer 6, and something's gonna happen. Is that all right?
Okay.
All right. So I think this is about all the pictures I wanted to show from this blog post, and we can thus go through the PDF thing.
Wait, I'm actually not sure if it's clear. Like, we could add any random vector, and it would obviously change the output of it.
Yeah, this is a great question. This is exactly what the PDF covers.
Oh, okay.
So, yeah, maybe I answer that question first and go through the details later. So, like the above was a simplified picture, and what they actually do, well, I think they try to do what they showed before, but found that often it doesn't do the same. And the actual technique they use is they take a positive prompt and a negative prompt, and then they run the forward pass, and then they take a difference of the activations, and this is the thing they're going to inject.
So you're trying to like extract the thing that they need.
Yeah. So like in this case, this is like love minus hate, and like supposedly we get like
Just wedding.
this is actually weird, right? Because like if you just just word by word remove, then you will get like love minus hate, and the weddings will cancel out, right? I mean, you have yeah, but they find this is not what happens. What happens is, so like apparently, like supposedly, maybe like this thing gets like diffused such that in like a late enough layer, the activation, the representation like is yeah, I mean, like this is not linear. The representation will not be linear in the sentence. Like the weight will not correspond exactly to positions. And so, like, we get a diffuse representation of love about weddings, and we get a diffuse representation of hate about weddings, and like, apparently, love about weddings is different from general love enough such that this like differencing works empirically. Is all right.
Okay.
Okay.
Don't they actually like I just read some random papers about this stuff. But if I imagine like we have one vector, like I love talking about weddings, we have another vector, I hate talking about weddings, and this is like wedding direction. We subtract one from another, we get a like perpendicular vector, and then we like take 90 degrees from it, and we get the wedding vector. Don't they do this orthogonalization thing here? It would make like total sense with like vector spaces.
Right. I think this work does like only different thing. and does the auto-organization. Yeah, I think like I think they kind of went into a different direction. Um, yeah. So what else do you want to talk about here? I think we want to talk about their yeah. So maybe look at like this map of like again like a map of other work. So like you can patch weights, you can patch activations. Like this is like literally just like the place you insert your intervention into. And there are a few ways you can try to find the magic vector. And like you can fine tune the model. And what this work does apparently is they fine tune the model directly, and they have an original model, and they just differentiate the weights after fine tuning the original weights, and this is a patch, like pretty straightforward. Then you can try to apply optimization. So okay, I'm actually not sure what this does, so let's skip that. Then again, like I'm not sure what a truthy attention head actually is. Like so, like what they do is they introduce a metric on some attention heads and use that, and we just take the difference between activations at a given layer. Okay, so that's like just a map of some other work in the space, and speaking of organization, do you have like a date when it was popularized? Yes, I mean a year. Yeah, I'm also not sure. Like, all right. Okay, so another thing to cover here, which I'll try to do in a few minutes, just to like highlight some things. Highlight is evaluations, as in how they confirm that this does something besides looking visually. And so one result is as follows. We get a large text corpus, and like we for like say for every page in the corpus, we get the baseline frequency of wedding related words. And what we do then is we basically just compute baseline perplexity and patched perplexity. So like what this means is that we have this like NLP metric, which is the probability of a given sentence. I mean, like probability that this word is the starting word, and probability that this word is the second word given this word, and so on. So like just a bunch of conditional probabilities. This is perplexity. And so we have those, like we have a bunch of documents with wedding words, we have a bunch of documents without wedding words, and we are like, what does I think it's fine to leave it like that. And we're like, what is the baseline model's perplexity? And we're like, what is the patched model perplexity? And like, what is the difference? And if the patched model says that wedding words are more probable, then we did the thing, right? So like this literally asks if our patched model is like ascribes high probability to wedding words. on like an natural corpus. Yeah, and well, this is kind of the same, and another few pictures. So again, playing with the gun, aren't they?
Every time we have something, they're taking out the guns. Maybe we should actually like background check.
Right. Russian hackers, Georgian guns. All right. So I think this is the final thing to cover before taking a break. Like an important question to ask when doing this kind of patching work is if we are maybe bullshitting ourselves. Like, is this just prompt engineering? Like, do those like fancy activation patchings achieve something different than just like adding a sentence like "talk about weddings" in the prompt? And like what do the authors do to find that if this is the case? So well, this is going to be a little complicated, I think. So like here is like we have like two things to compare. One is we just add wedding into like the first layer essentially, and the other is that we and adding it at the first layer is the same as adding to the prompt, and we also added like somewhere deep. And the question is depth useful? And what we're going to do is we're going to look at table 5 apparently. What's table 5? Yeah, not useful.
I think you can do double quotes and it will search for this precise thing.
Yeah, maybe too precisely. Maybe it's in the appendix. So that's figure 7, whichever is table 5. Oh, I think this is something. Yeah. So what's going on here? We're adding the same vector. Actually, like not the same vector. I'll just zoom back and get back here in Jiffy. Like first introduce notation and then look at the picture. So like we have this notation to say that we take activations at layer on the left hand side and insert them into layer on the right hand side. Like for example, our baseline where we just add like a prompt is 0 to 20 for a 20 layer model.
Mm-hmm.
And if we get back to table 5, yeah. We see that if we get early activations and add them to the end, then we get like little effect, as in like a little anger. And if we get late activations and like apparently just increase them, like multiply them there. Oh yeah, like if you get late activation and instead of late, and we get a lot of anger. And like this suggests that depth does something. I think this suggests that that kind of like this is probably this old CNN adage that early layers like do some semantic processing and like diffusion and something. Or like yeah, so like they or maybe you can think of it like they encode something, and so like we need and the activations are only semantically meaningful after a few layers of encoding. Like you get a rich enough space to work in. Okay, so this is like one test to take an early activation and a late activation and test them. And yeah, so this maybe needs us to look at table 6. Let's see. Yeah, so like this is the perplexity experiment, so like the web text perplexity thing. But we again compare two things. One thing is we add weddings even earlier, so it's not an activation patch, it's a tokenization patch. So this is like even closer to straightforward prompting.
Before 0 layer?
Yeah. Even closer to straightforward prompting. And yeah, so this, let's take a look at table 6. Yeah, so I think what this experiment actually shows is that bad prompts don't work very well. I mean, so like they say that like their method gives us a better metric, and just adding weddings gives us a worse metric, where the metric is probability of something wedding related. But this doesn't say tell us anything about what if we found a better prompt, right? And you can actually get something useful from this, which is that this method might be easier to use than prompt engineering, right? And I think this is about all what I wanted to show besides this pretty plot. So what this plot does is we again like take I'm not sure like which patch that is. Yeah, but like maybe look at table 8. Yeah, so this is again wedding patch, and what we're seeing, like this compares the probability difference between the baseline model and the patched model. And we are seeing that Russians are not welcome at weddings, and like that brides are. Yeah, and this plot is a way to this plot. This I lost the plot. Yeah, so and this plot is a way to visualize that. Like we have the normal distribution on as has the red line, and we have a v at y-axis, which is why the normal distribution is flat, and like we see that a bunch of tokens becomes more probable, and a few tokens become less probable. Yeah, so I mostly wanted to show this plot because you don't often see an ordered mean log probe difference as a y-axis. Yeah.
So normal distribution is distribution of unchanged model, or some normal distribution.
Yeah. So this is normal distribution as like Gaussian distribution, as like standard normal distribution, and like and the blue dots are the difference between the patch and the baseline. And so like if there is no difference, we expect a flat line.
Do you have an understanding of why blue dots follow normal distribution?
Blue dots don't.
I mean, they seem to follow.
You mean like why they follow it for the most part?
Yeah.
Yeah. So
if you don't, it's fine. It's like
yeah, I think what's going on here is that like I mean each word actually contributes. So like I think like I mean one reason is that they are ordered, and this is why we have the negative ones at the left and the positive ones on the right. And then why is the magnitude like that? This is because these are probabilities. I mean log probabilities.
okay. I got it. Yeah.
Yeah, so a really interesting y-axis here. Okay, so let's do a recap and then make a break. A recap of what we just talked about for like 50 minutes. So we talked about the different ways to do interpretability on transformers, and like I think one thing I didn't highlight is that interpretability is actually threefold. As in, interpretability is kind of the same as steering, because if we know where this thing is, we can patch it. And then we covered this like wedding result, I guess. So like we talked about semantically interesting latent spaces, and then we covered this wedding result, which talks about patching activations with a vector which we distill from activations on two dipole prompts. Yep, and this concludes the first part. In the second part, I'd like to talk about the actual Anthropics thing. So, like, continuing on to the second part, you can kind of brace yourself because we covered like that much, and apparently there is like the entirety of screen to go through. I will do our best to get us through this in an hour. Okay, so like we have two kind of to get to the results we are like aiming at. We need two kind of conceptual prerequisites. One conceptual prerequisite we already covered. This, I think, the technical term for this is kind of like a continuous representation, or like, well, basically like continuous state space. This is obvious for pictures because pictures are like, you know, like pixels and like real numbers and like a grid of real numbers, and this is like continuous, fine. This is less obvious for words because words like don't have an inherent space, but empirically this works and works in fun ways. So like continuous state space we have. And here is another idea, which is going to be like a little weird. So weird that, yeah, my scroll falls down for a bit. So like consider that like we have like data of given complexity, in which case complexity means like real dimensionality, like how many real axes we need to represent the data accurately. And we have a model of given complexity, which is again like real dimensionality. And like sometimes, like if we have two numbers, like real dimensionality of data on the model, we can have like three kinds of relation, right? So like less than, equal, and greater than. If we are greater than, then we are good. The model is over-parameterized. It's maybe not what, like it might be inefficient because it's redundant, but it's all right. If we are equal, then we are probably in the best possible situation. If we are less than, then we are going to get like increasing model error. Uh, and there is a hypothesis that what current neural networks do to cope is they use this trick of almost orthogonal directions. So, like in a simple world, you would use orthogonal directions always. But if the data is more complex than you can fit, then you can at the cost of some error use almost orthogonal directions. Is that all right? Yeah. And this is called the superposition hypothesis. And I think it's interesting to ask, like, we were just talking about nice things. Like we were just talking about like this very simple representation where like we just go like constant distance and get something useful, and we go another constant distance and get something useful again. And like, why the hell are we for dramatic effect? Let me actually find the full picture. Oh yeah, and like, why the hell do we get square anti-prisms all of a sudden? And I think, like, this is like a question you can contribute. I have two main ideas. One is that word2vec and like 2012 style embeddings are low dimensional as compared to current embeddings, as in like 300 as compared to 1600 and much more than that. 1600 is GPT-2. The other idea is the objective function. That is the function we are minimizing. Like, it would seem that that depending on your choice of function, you can push features to be orthogonal. I think L1 regularization is famous for having this property. And yeah, and it so happens we train transformers with objective functions which are prone to superposition. I mean, NLP transformers. That's important. Yeah, I think this is the main reasons. It might also be that superposition occurs in deep networks because word2vec is a single layer network. Though I think this is empirically, well, at least like the authors induce superposition artificially into a shallow network too, but I'm not sure how, like, if what happens in like in real life. Okay, so like two premises: continuous state space, superposition.
What is sparsity here? Like, what do these percent mean? Do you understand?
I would kind of like to well, we do have a compact thing. Yeah, so what sparsity corresponds to is like how many features are there and how many of them fire for any given input. So like if you have 100,000 features and only 2 of them are active for a given input, this is a very sparse network.
Okay. So this kind of relates like sparsity of like vector spaces and things like how much do we have in like area that activates from input?
I'm not sure. I see.
Okay, it's fine.
All right. Yeah, so like, but this is basically like a particular feature of our space, which relates to like compression.
Okay.
Also, I wonder if compre. Yeah, we might get back to this in like a few paragraphs. Okay, so there's also this like fancy argument which I'd like to reproduce that features are useful to understand and interpret because features are robust against the chaos of dimensionality because features are axes which scale with the number of axes, and the space they cover scales as their exponent, right? Because it's like the volume of the space. So trying like to figure out like parts of the space is should like will inherently be more cursed than just figuring out the axis. Cursed is complex. And so we were talking about like what is a feature? Like, is a neuron a feature? Is a circuit a feature? Something. And for this work, we do want a feature to be something human interpretable, but we don't want to constrain ourselves too much to our prior understanding. Like, for example, so we were talking about virtuology and attention heads, and there has been work about trying to take like a golden data set annotated by linguists with like the right syntactic structure and trying to see if transformers like match that. And like the results are that they match some of that and some things they do in a different way, and we don't want to discard the different way because, like, for instance, if we are training like a biology model, we might actually learn something new from this compression. So this work, what it does, it takes the feature to mean a direction in activation space, and like the way I write this, like the way the authors write it, is that so we are talking about the linear layer here. So not attention, the linear layer, and what we do is we basically take like the linear layer, which is wx, and we try to like to split it into chunks, which will be directions in activation space. So we, when we say a feature, we mean a mask which we apply to w and x, which gets us the like a part of the activation space. This is a technical thing which I think I'll skip now. So like, okay, we defined a feature, and the question is how to operationalize that. Like, how do we actually find those features? And what you're gonna do, so like this here is a picture of the transformer again. So like we have attention heads, and then we have the linear layer. And we are going to train another model on the output of the linear layer. And this model is going to be designed in a very special way. It's going to be an autoencoder, and like what you're gonna do is we're gonna try to learn. So like this is how we operationalize feature as something learned by the autoencoder. So like basically like we say that we are trying to reconstruct X, the linear layer output, as so like we had the original computation as WZ plus B, and we are trying to learn sum of f of x plus b. So f of x, these are those like these are those wx chunks.
Mm-hmm.
And I think I don't have loss here. Yeah, I don't have loss, but basically we are minimizing reconstruction error. So like just the difference between x hat and x.
Okay, so the idea is that you want to train such network that we have our original network, which just has this big W weight matrix. I want to make another model which will have like different matrices, each corresponding to the feature of the original thing that will like. So instead of having like one big matrix that we don't know what to do with and can't interpret it, we have like a lot of small ones, and this sum is just like summing results all of them up.
Yeah, that's correct.
Okay.
And there are like two keywords to throw in here, which will maybe help something. I think I'll start with the one which makes more sense, which is that apparently doing this kind of thing is like has been invented in the 70s and is called sparse dictionary learning. Yeah, so like what we're gonna do is we want to encode our input, in this case our the output of our linear layer, as a sparse linear combination of something, not necessarily orthogonal something. Like this is yes, I think the question here is like what is a dictionary? I think we're going to cover what the dictionary is on on this next picture here. But yeah, but like the basic setup is encode as a sparse linear combination of not necessarily orthogonal features. And like this is like something one, and this like there is a kind of exciting connection here to DSP, because like what this thing does is it learns as a dictionary, and what we used to do in DSP is to use standard dictionaries. And yeah, so this is like assumption one. Assumption two is, I'm not sure if this is actually the right thing to
dictionary is like a map to a sparse space.
Dictionary is the non-orthogonal elements, so it's not the map itself. I think the map is actually maybe that is right. Yeah, I think in terms of this setup, R is the elements we are mapping to, and dictionary is the map. Yeah, that's right. Okay. And there is another result, which I like for the depths of which I was totally unprepared when I was looking through the materials. I think we'll just go with with the first screen. So we have the sampling theorem. What the sampling theorem does is it shows that if the signal is bounded, then we have a nice interpolation. That, like, if the signal is bounded, then this this gives us a perfect interpolation with like a given number of samples. I think this is so, like this is this translates the bound on the signal frequency into the bound of the number of samples. I think something like that. Yeah. And there is another result about perfect compression, I think, which says that if we know that the input signal is if we bound the input signal sparsity, then we can reconstruct it perfectly with an even smaller number of samples, something like that. So like one bound gets us from frequency to number of samples, another bound gets us from sparsity to number of samples. And all this is to say that these are kind of very fuzzy intuitions about why this setup in particular. Like, why do you want sparsity? Because it seems because I think I think we want sparsity because it has nice technical properties, as in like it's easy to work with, and because it seems to work in many domains. Basically, sparsity is not the only approach to encoding here, but I think the authors chose it because it seems broadly nice. That's the way I read that. Yeah. So let's kind of try to see what we get from this encoding. I wonder if I should look up the original. Yeah, so that's the paper. Yeah, maybe not. Maybe continue with my picture. So like we're kind of skipping some implementation details and looking at what this yields us as a setup. So we get depending on the size of our encoder, we get a number of features, and for each feature we record the we record the neurons in the MOP by how much they relate to the feature. And I'm actually yeah. So like basically we see the related neurons. Then we plot activations. Why it's interesting to plot activations is because some features are going to be like like this feature is kind of like the expected thing. Like in most cases, it doesn't activate, but you would expect some features to be very general. Like maybe a feature for English language is going to be activated a lot of times, and this is a feature for Latin, so maybe not very often seen in the dataset.
Wait, so this plot, what's X, what's Y?
Yeah, so on the x-axis, we have number of activations.
So how many times did it activate in some like data sample?
Yeah, actually, now that you asked it, I'm confused as well. Yeah, so we fix a feature, and yeah, so this is like number of samples. So this is a histogram. So like in 250 samples, the feature activated 0 times. In 25 samples, it activated 2 times. You're asking why is it smooth?
I generally just don't understand this graph, but it's fine. Plot, I know.
I mean,
if it's not critical, we can move on.
Well, I mean, I think it's what that happens here is that in 250 samples it activates 0 times. In 25 samples it activates 2 times. In
okay, I got it. Okay.
Right. Then we have correlated tokens, and like I guess American tokens are discorrelated, like Dolores Citamet tokens are correlated. And this is the probability distribution overall over tokens. Oh wait, I can actually color it. What's going on?
You can just select it.
Okay, that's weird. Okay. And
why would American tokens be discorrelated?
I expect this to happen because those are overrepresented in the dataset.
Oh, okay.
Yeah, and we get like top sequences which activated the same. And yeah, so like what's going on here? We took linear activations and we compressed them into and we kind of found those like masks which correspond to directions in activation space. And then like we took those masks and we just took the top tokens which correspond to the mask, and we are like, okay, it seems to do something. And you can see the auto interp explanation here. Auto interp, actually, like when I first saw this picture, I was expecting something more impressive, but auto interp is just Claude asked to explain what the hell that is. I mean, I think the design is literally like just give it like top negative tokens, top positive tokens, and like explain and like score confidence. Yeah. And so like this was like a qualitative evaluation. If you try to do quantitative, we get that for each token, like we train a small autoencoder, a medium autoencoder, and a large autoencoder. And if you go through all tokens, we see that the average number of features active is large, actually, but not extremely large, so like fewer than 300. And the autoencoder, even the small autoencoder gets us 2/3 of the signal. So like our reconstruction is like two-thirds this term and 1/3 noise, which isn't very impressive, I guess, but maybe this is for the smallest one. Yeah.
So it means that like 2/3 of the stuff that's activated like found a feature for it. And then some other stuff it's like we don't know what the feature this corresponds to. Like I couldn't explain it with our map.
Yeah, that's right. Yeah, so I was really curious to see what the number is for the large autoencoder, because like if 2/3 of the large autoencoder are like just are not just sparse but dead, as in not active on over 10 million tokens, then you would expect it to explain much less. Well, I mean, much more. Yep. So like, but this says that like this kind of works. Not really works, but kind of works. And this is actually still not the last result. I mean, this is the previous result. Oh no, actually, yeah, I'm sorry. This is the previous result. Yeah, this is actually a previous result, which worked on the toy model. And we have yet to get to the practical model. Here's another fancy picture. I think this one is actually from the practical model.
So from the news.
Yeah, but the approach is the same, basically. So what's going on here is we have we plot probability density on the y-axis, and we plot feature activation on the x-axis, and we name this feature the Golden Gate Bridge. And what we see is that like this is actually the proper way to view this plot. like the like approximately all data points are irrelevant, but there is a fat tail. So let's zoom into the fat tail. And like if you look at the left hand side, which is like low activation level of this feature, then what we are seeing is some bridges which are related to the Golden Gate Bridge, like has similar coloring to the Golden Gate Bridge, or like like tourist instructions, something like crossing the Golden Gate Bridge, something. And if we go to high activation levels, we are seeing the same, like in all its glory, like yeah, yeah, sure. So this again like suggests that this does something. Like if we get high activation, we get this thing. If we get low activation, we get something which is related to the thing but not the thing. And supposedly, if we push even less, like even more to the left, we get something which is even less the Golden Gate Bridge.
So again, asking about this as well. What's to the right is what activates more.
It is yeah. So this is actually what is that? So yeah, I think this is like this is magnitude of f of I. Yeah.
Okay, and what does density mean here? Is like
it's
what's on the y-axis?
Yeah. So I think this is basically count of data points.
These graphs they would, I think, benefit from like inverting them, because usually it's like other way around. We have like number of data points on X, but okay, it's fine.
Oh, I think they wanted to show like the power law. All right. Let's see if we want to mine anything from the latest thing. But I think probably not, actually. Maybe just some more pictures. Yeah, let's just look at some pictures. Because we went through the methodology already, which is similar here as in the previous work. Okay, so like here is that on the left hand side we have baseline. On the right hand side we have patch. Where patch is just like patch this feature activation to whatever to whatever is on the slide. And like the baseline Claude is like, I'm an AI. I don't have a body. And a patched Claude is like, I'm the bridge.
Wait, I actually think I missed. So, like, backtracking a bit.
Yeah.
We talked about that the very first ideas of like how can we patch this thing. We like acquire a couple of vectors, we like subtract them, we add them to this activation functions.
Yeah.
Then we moved on to like we can find the features. How do we actually patch?
Yeah. So I think we just swap x for x hat. Yeah, so that would be the baseline. I mean, so like we have this linear layer, and we have this like substitute linear layer we learned, and we just kill the linear layer and use the substitute instead.
Oh, okay. And then in substitute, we just like multiply by constants.
Yep.
Okay, good.
Okay, so like, and we can do this across a number of features we found. And they're like, what's the most interesting science? And it's like physics, and they're like brain sciences. It's like, yay, brain science! It's a profound frontier. And you're like, what should I do? It's like, take a walk. And they're like, patch, and it's like, go to the Eiffel Tower. It's a must see. And so like, uh, oh yeah, this one is fun as well. It's like, how do I get to the grocery store? Like, walk. And if you patch, yeah, let's walk across the bridge. And another thing interesting to look here, like like another interesting picture to look at in the results is they find like these were kind of simple features in some sense, as in like we can describe them in 2-3 words. We also have complex features, as in we can't describe them in 2-3 words. So like this Python function has a typo, and what color does, it means this feature activates on these tokens. The redder the color is, the stronger it activates. And it's like, hey, you have a typo. And we're like, is this a Python feature? And we try this on C, and it's like activates here as well. And we tried it on Lisp, and like activates here as well. And we're like, okay, is this a typo feature? And we try it on plain English, and it's like, no. And we're like, but is it a typo in code feature? And they're like, try division by 0. And it's like, hey. And this is how Anthropic research days go. Yeah, so, and empirically we find that that's what it does.
We need to make a meme like, this is real machine learning done by real machine learning scientists. It's just like picture of Anthropic like person just like.
Yeah. Yeah, I think this. Yeah, so there's a bunch of technical details which I will skip. Another kind of interesting thing here is visualizing the feature space. So this is very similar to what we were doing here, like in those old style embeddings. What happens is that you also have like related words close by, as in like woman will have a girl nearby, and like stuff and things like numbers will be nearby. And so let's do the same on a more advanced model. And we're going to use standard dimensionality reduction to go from a high dimension embedding of the autoencoder to G space. And if we do that, here is what's going to happen. Yeah, so
Hills are close to landmarks.
yeah, hills and landmarks like Statue of Liberty, Eiffel Tower, Statue of Liberty, Eiffel Tower, tourist attractions, and then like bridges.
Wait, but Golden Bridge was somewhere up.
Yeah, apparently Golden Bridge is closer to San Francisco than it is to Statue of Liberty.
But it's just a 2D map. Yeah, it's a 2D map. So
yeah. Also, maybe interesting to kind of zoom in some more. Yeah, so like earthquake region. Apparently, like how one particular town copes with earthquakes and like stuff and things, and like, yeah, I don't know.
So wait, that's correct. That's a 2D map. They couldn't like they have chosen.
Yeah,
It doesn't show anything.
I mean, yes.
We could make any of them like nearby.
Yeah. They could have chosen any particular projection. That's correct. I think I kind of failed. Also, we have an interactive map, but like so. Two things I kind of failed to say. One is that apparently this was the neighborhood of Golden Gate, which is like we did center the map on Golden Gate, and I mean, and they say they use like a standard projection metric, like UMAP is a standard projection. It's kind of like it's similar to TSME. And they claim that if we center on something else, we get something like vaguely kind of something. In this case, we center on immunology, and in this case, they helpfully provide cluster annotations so that we don't have to fail to find clusters. So like common cold and flu and like stuff and like common diseases and like autoimmunity is a different cluster, and so like something's going on here. And the interesting result is that this works at all. Because like this is something very neat where there is little a priori reason kind of to expect something very neat. Also, this is kind of fun for, because of the topic. It's kind of like map of inner conflict space. So like, yeah, exactly.
We should show this to psychologists, or maybe we shouldn't actually.
Yeah.
So there is an interactive thing you can like choose your own.
Yeah, I can. Maybe inner conflict again, and like uncertain how to proceed, and this is like this isn't particularly interesting. Yeah, so impossible choices, like no way to win, lose-lose situation. There is no actual way. Yeah. Yeah, so the interactive thing you can find if you go to the latest paper and Ctrl-F UMAP.
Was there feature compress? The title.
Completeness. Yeah, so the question is like, do these features in some sense cover like all, like we pick a topic and we get top 5 features, and we are like, do those features cover the topic completely, or is there something missing? Well, we ask a human rater, and oh my, I'm not actually sure if it's going to relate. Yeah. Yeah, so I didn't look at this graph before, so I'm not sure what it does.
What's there in the like find text?
It's
Oh, it's different capital name.
Yeah.
Yeah, they are rare in two sentences.
I'm glad is the okay. That's an interesting result on topic.
Right.
This is real machine learning research made by real machine learning scientists.
Yeah, so I was hunting for a plot which would show us the like top 5 features and completeness, but I kind of don't see it. Yeah. I think what they meant to say here is that like we get like we have dataset frequency and we have feature frequency and and yeah. And apparently, the more often we get something in the data, the more features correspond to the thing with a sigmoid. All right. Yeah, so there is like another like 20 pages of examples. Yeah, so I encourage you to examine them on your own time, especially if you're an artist. And I'd like to talk about the implications of this. So like, we covered a lot of ground today, but the like our like the very latest result we are meeting today due to is actually somewhat small as compared to what we covered. As in, the latest result is basically an application of the techniques developed previously to GPT-3 class model, to like a 7B class model, and like it's like the article is long because they do like a large scale evaluation and look at a lot of examples, but they don't actually introduce many novel techniques. So like the core claim is that we have a superposition in linear layers of the transform architecture, and we can unpack this superposition, which is like this non-orthogonality, with a sparse autoencoder, and this scales to this size of the model. And this is useful because we can both interpret the model and steer the model with that. Those are dual kind of, because when you know the part of the model which does the thing, you can patch it. And I think it's also like I just wanted to highlight one special way to steer a model, which is I think also by Anthropic. It is unlearning. It is when we like the idea is basically like to kill all model internals which relate to a particular something, like to bombs. You like basically like just mask them out, like zero them out, something them out. And if you have high quality features, this is easy to do, right? Right. And like a few directions where future research might go from here. So, like, first off, I want to say that this is a very special design. Like, this is a very special design because of the like sparse over complete autoencoder. This like they could have chosen something else here. And the second reason why this is a special design is because they focus on this box, and there are many boxes here. Like they have reasons for choosing this box in particular, but like many boxes to choose from. And so one of the things which is currently unsolved is attention superposition, because we expect attention to have the same thing with orthogonality. This is like a straightforward direction to go to next. Another straightforward direction is to just scale the thing, like make it work on a 70B class model, not a 7B class model. And like the non-complex like a non-trivial direction to work in would be to focus on different boxes. Indeed, one of the other trendy interpretability methods which is currently out there is representation fine-tuning, which patches residual connections and not linear layer outputs. Yeah, so I think that's it. And we're done. So thank you.